A very good afternoon, ladies and gentlemen. I welcome you back here at the Technical Forum at the group exhibit Hydrogen Fuel Cells and Batteries. We are here at the Hanover Fair in the year of 2016. I welcome all of you to come and have a seat, have a drink. They are all on the house to enjoy the next discussion together with me. Our next topic will be the system automation of PEM fuel cells with prognostics and health management for improved reliability and economy. For that, please welcome with me representative of the SAPPHIRE project consortium, Mr. Federico Zenith. Big hands, please.
Thank you. Does it work? Yes, thanks everybody for joining in. I'll be presenting this European project that is coming to an end just in these days. In fact, this is the last week of the project, and we are therefore presenting the results. Some outline of my talk. First, a little bit introduction for micros combined heat and power systems, then about diagnostics, and prognostics and control, which are the main topics of the project, and finally about rejuvenation of fuel cells, which is a topic we, so to say, we stumbled upon. For introduction, SAPPHIRE is a European project financed by the European Commission. A budget over 3 million euros, of which 1.7 by the Commission, and it is a project developed across 5 countries, Germany, Norway, France, Croatia, and Denmark. In Croatia, FESB University Split worked on the diagnostics of fuel cell. Prognostics was a task of FC Lab in France. SINTEF, which is my institution, work on control and on the coordination of the project. IFER in Germany worked on the protocols and on the interface between the system. ZSW again in Germany on stack tests, and they also produce stacks. There are some of their stacks actually on show at the booth D73 if you want to come. And Downturn Power worked on system tests, and they provided the micro CHP system we tested. We have, of course, a website, and if you want to visit the website, you can also find all our public deliverables. Very shortly about micro combined heat and power systems. Why are we interested? The fact is that chemically the exergy inside natural gas is quite high, and burning natural gas for heating water is a sort of sin. It's almost as bad as using electricity to heat water. So you really want to do something more useful with that, and one thing useful that you can do is to produce electricity, and that's why you have a business case for micro CHP systems. You start here from the first case when you have a normal natural gas burner that most people in Germany and other countries have. You have a demand for heat, and you fulfill that demand with energy from gas. In the micro CHP system, you still fulfill the same demand from heat, but use a converter that has an efficiency of about 50%, which means you increase your consumption of gas, in fact, and then you produce electrical power. With that electrical power, you can sell it back to the grid, and since the price of electricity is higher than gas, you can make money out of that, and that's where your business case is. This is what a typical micro CHP unit looks like. You start from the left with water and natural gas from the grid. They go through a fuel processor. They are reformed by heat and other reactions into hydrogen and CO2. There is some trace amount of CO that are dangerous for the fuel cell. We add some air bleed to remove that. Then the hydrogen goes through the fuel cell, produces electricity, and then what is left of the hydrogen is used again and burned in order to generate the heat that again fuels the fuel processor. Then all the exhaust is then sent to a cogenerator on the right that collects all the heat from the system and provides the heat that the house requires. Then the produced electricity is normally sold back to the net. Typical size is about 1 kilowatt in heat, 1 kilowatt in electricity. Some definition about prognostics, because a constant is that people don't get very much difference with diagnostics and prognostics. Diagnostics means, in brief, to explain the present based on the past, and prognostics is predicting the future based on the present. Generally, you run first diagnostic to understand the condition your system is in, and then you run prognostics in order to understand how long the system will run in the future. This is something that is very common in aerospace, in also mechanical engineering, and in general, wherever you have expensive systems that you want to maintain in a timely fashion. So oil and gas, for example, is an area where they're applying prognostics recently, and also fuel cells, of course, which is what we want to do in this project. Okay, so for the diagnostic part, there are many ways a fuel cell can degrade. Some are reversible, some are irreversible. For the reversible part, you have too much water, you can have too little water. This is, of course, relevant for PEM fuel cells, as you have other modes of degradations. You can have a poisoning by carbon monoxide. Irreversible degradation is typically due to degradation in the catalyst, the by particle aggregation of loss of support, or by membrane damage. And all these degradation modes have one thing in common. The only thing you normally read in a system is that the voltage is decreasing. So you cannot really immediately understand from the voltage what the problem is. I sometimes compare this to a crying baby. The fuel cell is giving one signal, and just like crying baby is not really telling you what the problem is. You have to figure out for yourself, and that's what you want to do. One way to figure out what the problem is to run electrochemical impedance spectroscopy, or EIS. This is very popular in academia because it gives you a wealth of information, but it's not something you can commercialize because the equipment for EIS is generally more expensive than a micro CHP system. So if economy has to make sense, you would rather buy a second micro CHP system. So there are some projects like Decode, which is another EU project that aim at including these EIS in converters, but they're not commercial yet. But until they're commercial, we have to do by with whatever we have. One thing that was done at the University of Split that was very interesting was the possibility of expanding the standard equivalent circuit model for fuel cells with these two elements on the extreme right and left there in the bottom figure. Those are resonance circuits, and they have the characteristic, of course, of fitting better the image you see on the top. And the most important thing is that that resistance at the right, R4, is actually a very good prognostic variable, in the sense that as the system is further and further degraded, that resistance increases gradually in value. And that's one way you can tell what the situation is in terms of degradation. For prognostics, this has been developed at the FC Lab. It's a model maze prognostic model. It has a number of parameters, and some of these were excluded because there were a lot of parameters, so there was a selection. And by estimating the aging of these parameters, it was possible to realize a model that is able to predict very well the aging of fuel cells. In this graph here, you see in green the actual measured values, and in blue the simulation. And the blue line is based only up to the second spike you see there at about 50,000 seconds there on the left, or 0.5 in the scale as reported. And the rest is a ballistic prediction. So it's a very reliable model and has worked very well. For the control, we had developed a number of control techniques. One I like especially is the control to adapt the air bleed level. Normally you have a certain percentage of air bleed coming into the anode side of the stack together with hydrogen in order to remove the CO. But this is constant and normally set for the worst case, so it's a bit of a waste. And the problem is you cannot really measure the CO interactively because it's very expensive. Again, it's a chemical measurement. And at the same time, the dynamics of CO poisoning are very slow. They take several hours to complete. And you cannot really tell when there is a CO poisoning because the effects are not immediate. What is immediate, though, is the effect of air bleed when you increase it. If you have CO poisoning and you add some air, you immediately see the voltage increase. And that's what we exploited. So the way it works is that we increase the air bleed a bit, then we see the voltage increasing, and as long as the voltage is increasing, we increase the air bleed, and then we stop and we gradually reduce. We have tested this, and we can say it has been demonstrated over several thousand hours, and it works with some problems that are going to be sorted out soon. Another problem is the humidity. We normally want to run a slightly higher 100% humidity in a fuel cell, but the problem is that in order for this to work, we have to keep a very stable temperature. And if the temperature deviates a bit, you can have problems with too many droplets forming, and this causes an unstable voltage, or no droplets at all. And if there's no droplets, then one thing you notice is that the pressure drop reduces rapidly and becomes very steady. So in order to detect these conditions, in the case of flooding, we look at the voltage, and we see oscillations and a high standard deviation. We deduce it's a problem with flooding. And if we see the pressure drop becomes very steady and not noisy, then we deduce it's a condition of dry out. This has also been demonstrated, but it's not such a common condition, so it's mostly demonstrated in laboratory. A concept we developed, we could not test it unfortunately, was the ability of monitoring the lambda, the reactant excess ratio in a fuel. And the motivation for this is that if you run a micro-CHP system efficiently, you want to run it at a very low lambda, fairly close to 1. But if you go below 1, you run into hydrogen starvation, and within seconds, your stack will be degraded and useless. So you want to have a very precise monitoring of this. Again, you don't want to install a composition measurement, which is expensive. So in order to measure that, we found out since we have a burner downstream of the anode, the fuel cell effluent is burned, and the temperature of the flame is a very good indicator. So you have a very clear indication that you might run into starvation. And then, of course, what happens if you see the temperature of the flame falls down, the first thing you can do is immediately to reduce current to avoid immediate damage to the stack. Implementing prognostic in control is not immediately obvious because if you just try to optimize the RUL, the residual useful life of the system, and give the optimization problem to a computer, the computer will give you the trivial answer: don't use the system. And of course, that's not the answer we want. So one important part was defining a good formula to optimize. So for example, in words we can say we want to optimize the work we get done or the money we get out of the system over its lifetime, not just increasing the lifetime per se. One problem we encountered is that we don't really have that many variables to optimize for. For example, temperature is very constrained, current is often given, but we are going to start a new project next week actually. It's called Giant Leap, very similar setup, and we'll apply this to automotive, and that we expect to be much more fruitful. Finally, on rejuvenation, we found some very interesting results, almost by mistake. This is the actual data from a 4,500 hours demonstration. Normally, the degradation rate you measure is 2 microvolts per hour per cell, and we measure 0.2, which is actually the world record as the lowest degradation. And the reason was the system kept crashing. So we found out that if you restart the system often, you improve the degradation rate. And the second system, actually, we had the rejuvenation of 4 microvolts per hour per cell. So the system was actually improving over 3,000 hours. Finally, what are we going to do with this? We have developed 2 patents. One is already filed, and another one for data-driven prognostics is going to be filed soon, and so I cannot tell you anything about it. Dent & Power is probably going to implement this improved control system in their products sometime next year or later. Software will be probably made available on our website next month as the project is concluded. And ZSW will develop new stack designs from the results. So, conclusions. We extended the EIS model and found appropriate prognostic variables. We have developed several precise and reliable prognostic model. We developed control loops for carbon monoxide poisoning, humidity, etc. And all this was with very cheap and minor modifications to the system. And most importantly, we found out that a lot of the irreversible degradation in fuel cells is not that irreversible as we previously thought. So we have to study more. And finally, thanks to the European Union and to the Norwegian Research Council for funding all this. Thank you very much.
Thank you also from my side. Are there any questions from the audience at this time? Okay, all the questions can be taken to the booth. The booth number is D73. Once again, thank you for this very interesting insight on the project. Mr. Federico Zenith. Big hands, please.
Thank you.
Our next topic will be only in short minutes, only 2 minutes, and then we'll hear Dr. Ruven Henkel, and he will be representing the Eisenhut GmbH. We'll hear new aspects for bipolar plates and gaskets for fuel cells and redox flow batteries. Only in 2 minutes' time. Thank you.